Today we're going to spend time in class working through various problems. So we'll spend today's lesson reviewing various concepts. Let's start with the concept of an open set. Let's say that I, going from A to B, is an open interval. Then there exists real numbers p and epsilon such that our interval I is in the form v sub epsilon of p, which consists of those real numbers x such that in absolute value x minus p is less than epsilon. Let's say that capital A is a sequence consisting of real numbers x sub n. Then the limit, as n increases without bound, of x sub n equals a real number p if and only if, given a positive epsilon, we can find a delta such that x sub n is an element of v sub epsilon of p for all n greater than delta. We'll say that a subset O is open if for each point P in O, we can find a positive epsilon such that V sub epsilon of P is contained in O. We've seen that any open interval I from A to B is an open set. Let's say that O sub lambda is an arbitrary family of open sets for an indexing set capital lambda. Then the union of the O sub lambdas is also an open set. Similarly, let's say that the collection of O sub lambdas is a finite collection of open sets. Then the intersection over the O sub lambdas is also an open set. Let's say that capital S is a subset. We'll say that a point P in S is an isolated point if there exists a positive epsilon 0 such that the intersection V sub epsilon 0 of P with capital S is the singleton set P. That is, if there exists a neighborhood of P whose only point in S is P itself. We'll denote I parentheses S as the collection of isolated points of S. We say that a set S is discrete if every point P is an isolated point. We'll say that a real number P is an limit point for S if, given any positive epsilon, we can find an x sub epsilon in the intersection V sub epsilon of P with S, and x sub epsilon does not equal to P. Notice that we do not require that P be an element of S. We'll also call P a cluster point for S or an accumulation point for S. We'll denote L parentheses S as the collection of limit points of S. As a theorem, every point in S is either an isolated point or a limit point. That is, S is contained in the union of I of S and L of S. Moreover, no point is both an isolated point and a limit point. That is, the intersection of I of S and L of S is the empty set. L of S is contained in S. That is, every limit point of S is a point in S, if and only if every Cauchy sequence in S has a limit also in S. As a couple of examples, let's consider either the open interval from A to B or the closed interval from A to B. Then S has no isolated points, and the limit points is just the closed interval from A to B. Again, let's say the capital S is a subset. We'll denote the interior of S as S superscript circle as the set of points P and S such that there exists a positive epsilon such that V sub epsilon of P is contained in S. We'll say that our subset S is closed if L of S is contained in S. That is, every limit point of S is a point in S. The closure of S we'll denote by S bar is the union of S with its limit points, S union L of S. The complement of S, denoted by S superscript C, is the set of real numbers x that are not elements of S. The interior, S circle, is an open set. The closure, S bar, is a closed set. And S is closed if and only if its complement, SC, is open. Moreover, any closed interval from A to B is a closed set. Let's say that S sub lambda is an arbitrary family of closed sets. then the intersection over the S sub lambda is also closed. If the collection S sub lambda is a finite collection of closed sets, then the union over the S sub lambdas is also closed. Next, we have the celebrated theorem of Heine and Borel. It says that the following three statements are equivalent for a subset K. First, every sequence contained in K has a convergent subsequence whose limit is in K. Second, K is closed and bounded. And third, if there exists a family of open sets O sub lambda, since that K is contained in this union, then there exists a finite set, capital theta, inside of the indexing set, capital lambda, since that K is the union over the O sub lambdas, where lambda comes from this finite indexing set, capital theta. That is, every open cover of K has a finite subcover. Any subset K satisfying either of these equivalent definitions is said to be a compact set. If K sub lambda is a family of compact sets, then the intersection is also compact. If K sub lambda is a finite collection of compact sets, then the union is also compact. Finally, we have the so-called nested compact set property. Let's say that we have a collection of non-empty compact sets, since that Kn plus 1 is contained in K sub n. Then the intersection over the K sub n's is a non-empty compact set. Let's say that A and B are non-empty subsets. Then the following two statements are equivalent. A bar intersect B is the empty set, and A intersect B bar is the empty set. This is the same as A intersect B is the empty set, the limit points of A intersect B is the empty set, and A intersect the limit points of B is the empty set. Any pair of non-empty subsets A and B satisfying either of these is said to be a pair of separated sets. Let S be a subset of the real numbers. Then the following three statements are equivalent. First, we cannot write S as the union of two separated sets A and B. Second, given A and B and S, whenever P is a real number between A and B, then P must also be in S. And third, for any non-empty subsets A and B, satisfying S is the union of A and B, and the intersection of A and B is the empty set, we can find a Cauchy sequence contained in A, whose limit is contained in B. Any subset S satisfying either of these three equivalent statements is said to be a connected set. Otherwise, we'll say that S is a disconnected set. We'll say that S is totally disconnected if, given two elements A and B in S, we can find separated sets capital A and capital B, such that lowercase a is in capital A, lowercase b is in capital B, and S is the union of A and B. Finally, we'll say a few words about the Cantor middle third set. Let's start with the unit interval from 0 to 1. We'll call this C0. We'll now remove the middle third of the set to find the union of the two closed intervals from 0 to 1/3 and from 2/3 to 1. In this way, we'll have a sequence of subsets C sub n defined in a recursive way by just removing the middle 1/3 of the remaining closed intervals. In this way, we can express the limit as the collection of those real numbers x that have a ternary expansion, a sum a sub n over a sub k over 3 to the k, where the numerators a sub k are integers either 0 or 2. This collection of so-called Cantor numbers is an uncountable set. There are no isolated points in this set, and this set is closed. Hence, this so-called Cantor middle third set is a perfect set. Finally, the Cantor middle third set is totally disconnected. Thanks very much for watching this video.